Section 10.3, transformations that change size and similar figures. So in this section, we're going to essentially move away from rigid motion. So the shapes will be changing in some way. And basically what we're going to look at for the goals here, we're going to enlarge or shrink an object from a point P. So the size will definitely change. And then we're going to look at finding the perimeter and area of these similar figures. So even though we're going to change the size, the shape won't be changed. It's still not a rigid motion because we changed one of the things, but the overall characteristics of the shape will be maintained. It'll still be a triangle. Certain sides will be longer than others if that's the way it started, but it's going to be blown up or shrunk down. And I don't know how many people out there have worked with these. I'm pretty old now, but when I was a kid, we had these things called Shrinky Dinks. And they were like this plastic thing that you colored in, and then you put them in the oven, and the oven heated up and shrunk it down. And then you had this little plastic thing that looked kind of cool because the colors had compacted more from the shrinking, and it was just a little bit more brilliant. Anyway, I remember having those when I was a kid here and there, and my mom baking them for us. But at any rate, that's basically what we're looking at, either shrinking down or enlarging it. But after we do that, we want to find the perimeter and area of these new adjusted figures. And actually, there are a couple of formulas to do that for you. And then we're going to find the length of a missing side on what's called a gnomon. And we'll see what that's all about when we get there. Enlarge and shrink. So as I said, in this section, we're going to look at transformations that enlarge or shrink an object from a point P. The point P is called the center of the size transformation. The multiplier used to enlarge or shrink the object is called the scale factor, and they use the letter K to represent the scale factor. How do they work? Well, you find the distance from the point P to a vertex, and I'm going to just call this A for lack of a better word, or lack of better notation. So we're going to find the distance from the point P to a vertex. We're going to multiply that distance that we just measured by K, and then you're going to measure the new distance from point P in the direction of A. So you're going to either go towards A and stop short if you're shrinking it, or you're going to go towards A and go past it if you're enlarging it. And you're going to label that new point that you got from that new distance, scaled up by K or scaled down by K, A prime. And then you repeat this for all the vertices. So for example here, enlarge the figure with respect to the point P by a factor of 2. So I'm going to go ahead and start here with this point, call that maybe point A, and the distance is 1 diagonal worth. K is 2 here. So I'm going to go through A, I'm going to go towards A, but now 2, and end up over here. So the A prime would be right there. I'm going to do the same thing for point B up here. Let me see where I want to put that B. I'm going to put it right there. So point B, if we go up to it from point P, you can kind of see we go up 4 over 2. Up 4 and then to the right 2. So I'm going to double that. So from P up to B, I would actually go up 8 and then to the right 4. And that will take me all the way up to here, and this would be B prime. And if I do this one more time for point C here, we're going to go to here. There's 4 straight up, so I need to go 8 straight up, and that will take me to right here for C prime. And then when you connect the primes together, in this case there's 3 of them since we had a triangle. Oh, it's hard for me to draw on the screen like that direction. There we go. And then straight across there. This new shape that we've got, it's similar to the original. It's still a triangle. It has the same angles in the corners, but the sides are now longer. So we've scaled it up by a factor of 2. And if you look at the original shape, across the top, C to B was only 2 units. Now we're at 4 units. So the sides will all go up by 2 because of that scale factor. All right, so that's basically what you're going to be doing in homework, but it might be a different scale factor and different shape. I'll just connect this up here to show that. And then last but not least here, before we get into some other examples, looking at similar figures. Actually, gnomons will be last but not least. Sorry. But at any rate, looking at similar figures, they are figures that have the same shape, but not necessarily the same size. So what we do up here with this enlarging and shrinking, we created similar figures. They were the same shape, but they're not the same size. And side lengths and interior angles of similar figures are proportional to each other. So in the example above, they're proportional by a factor of 2. So for example, another one, if we had a square, pretend this is a square with a side length 4, then if we blew this up like this, and might not be a perfect square there, but let's pretend, and let's say this was a 6, the scale factor, so if you just are given sides for 2 similar figures, corresponding sides, the scale factor, you can get it by doing a fraction, a ratio. In this case, I want to know, let's say we went from 4 to 6, so I want to know what's the scale factor. 6 divided by 4 will give it to you, or 3/2. 1.5, however you want to think about it. So you always just look for the corresponding sides, and whichever's the new shape, you put that on top. Whatever's the old shape, you put that on bottom, and that'll give you the scale factor from old to new. So how do you find the perimeter and area of a figure that has been scaled up or down? Well, if P represents the perimeter of the smaller rectangle and P prime represents the perimeter of the larger rectangle, then the two perimeters are related by P prime equals K times P. So you just have to multiply the old perimeter by the scale factor to get the new perimeter. If A represents the area of the smaller rectangle or shape, and A prime represents the area of the larger one, then the two areas are related by A prime equals K squared A. So with area, you're squaring things, so it should make sense that the K gets squared as well. You're squaring that scale factor. And if you think about that in this example up above, if we have the perimeter, you've got 4, 4, 4 all the way around. 4 plus 4 plus 4 plus 4 would be 16, and then 6 is all the way around here, would give you a perimeter of 24, and 16 times 3/2 is 24. But now the area, when you do 4 times 4, you get 16. 6 times 6 is 36. So we actually need to multiply by more than 3/2 there. And if we square that 3/2, we'll get 9/4. And 9/4 times 16 will give you 36. So one of the ways to think about it is you're really thinking of this 6 as being equal to 4 times 3/2 over here. And this 6 is also equal to 4 times 3/2 over here. So when you multiply those two new things together, you get 3/2 squared times 4 squared, or K squared, the scale factor squared, times your original area. So that's why it works. Anyway, let's see what we got over here. So let's look at some examples. We got A and A prime that are similar. And we have a 12 and an 18. And they tell you to find some things based on given information. If the perimeter of triangle A is 32 feet, find the perimeter of A prime. So first thing you got to do is find the scale factor. We need that K because of the formulas that we're going to use to find the new perimeter and area, for that matter, in part B. They give me corresponding sides here. So I'm going to have 18 over 12, which reduces down to, nicely enough, or coincidentally enough, 3/2. So A prime, I'm sorry, yeah, let me do it this way. So A prime perimeter, kind of wish they would have used a different letter here, but we'll live. So A prime perimeter will be equal to the K times the A perimeter. And this will end up being 3/2 times 32, or 48 feet. So if the area of the triangle A is 48 feet squared, find the area of A prime. So the A prime area is going to equal K squared times the A area. And K squared would be 3/2 squared. And then the A area was 48. And when you work this out, you get 108 feet squared. So just using those formulas, if it's an area, you got to square the K. If it's perimeter, you just use the K as is. All right, and that's pretty much all there is to the similarity and what you're going to be doing with it. So for a gnomon, basically a gnomon is a shape which, when added to a shape A, yields another shape, A prime, that is similar to the original shape. So alternately, a gnomon is also the shape which, when subtracted from A prime, yields another shape A, which is similar to the original shape. So what the heck? So for example here, let's take a look at this shape. Say it's a equilateral triangle, and a gnomon for this would be a truncated little triangle part, or maybe a trapezoid, that when you add it on, you've created a bigger equilateral triangle. So this piece right here would be the gnomon. And if you start putting things together, if we say this original had A and B here for the side lengths, and then this was X and C for the gnomon stuff, the side lengths are going to be proportional between the original shape, this one here they'll shade in a little, and the gnomon adjusted shape. So you would have the following relationship. A over B is going to be equal to A plus X over C. And this will hold even if the triangle wasn't equilateral. If it was a different type of triangle, if you had those, the relationship between the sides, your gnomon, when you add it on and get a similar shape, you should have the same relationship where the this new longer side here, A plus X, should be related to A, and then B, this bottom side, should be related to C, and that's represented in that proportional relationship with those ratios. All right, so we won't be able to finish example 3 in this video, so please come back for part 2.